So this is at most 2n over epsilon rounded up to the nearest integer.
What is that in the denominator there? Sum over sum times?
Epsilon times the sum over 2n. Oh. So I'm just taking the definition of B and putting it in for B. Okay. And I rewrote some of the terms, but that wasn't necessary. Okay. And then see the sum cancels because we made B proportional to the sum. And so it's just 2n over epsilon. So for every fixed epsilon, this is just a linear factor. Okay. So if we plug that into this algorithm, then in time, order n cubed over epsilon, right? Because we're just taking the maximum value is at most 2n over epsilon, order n over epsilon, putting that in for A, we get an order n cubed over epsilon algorithm computing the optimal solution for the A hats. And what I claim is that that's an approximately optimal solution. That same solution is an approximately optimal solution for the original instance as well. Okay. So why is that true? Or how can we relate these new rounded off numbers and a solution in the new rounded off numbers to the optimal solution? Well, so say that we've got an assignment of jobs to machines. Let's define two quantities, or four quantities. So this I is going to be either 1 or 2 for machine 1 or 2. Okay. So load sub I of S is going to be the load of machine I with assignment S. Okay. And this is with respect to the original weights, but we're going to have a corresponding thing. So WRT is with respect to original weights. It's the same thing with respect to the modified weights of jobs. So is that clear? So what I want to say is that, okay, so how did we get the modified weights? We sort of divided by this normalization factor B, so, but then we rounded off the nearest integers. So what I want to claim is that this is very close to a B, 1 in B of this. Okay, or that. So the claim is that load I of any schedule S it's sandwiched between this normalizing factor B times the load in the new weighted jobs, and that same thing minus something that says at most epsilon times the optimal solution of the original problem. So the load of any machine in the new schedule, okay, is approximately this, the B time just proportional to the load in the modified schedule, but with an error that's small compared to the optimal solution in the original problem. Okay. So why is this true? It's just a matter of working through the definitions, which I just erased. Okay, but I think we can remember them. Okay. If we look at B, this normalizing factor, B times the load of I and S, is the B times the sum over AI hat, where I gets assigned, I should say J, gets assigned to MI in S. While the AJ hats were just AI over HA over B rounded up. Okay. Rounding up only makes things bigger, so that's bigger than B times the sum of HA over B equals the sum of HA is the load of the same machine in the original, with the original weights. Okay. On the other hand, this sum is at most B times this sum rounding up increases it by at most 1. Okay, so this is at most the sum of the original weights plus n times b, and we already saw that n times b is at most epsilon times the optimal solution. We picked b so that n times b would be at most epsilon times the optimal solution. So that's at most the load of I in the original schedule so okay, I just here I'm sandwiching. Okay, so here I'm sandwiching B times the load of S between two numbers. Here I'm sandwiching the load in the original. Okay, but if the inequalities are equivalent. Yeah.
I'm sorry, Professor, but can you please explain the part where you're standing right now?
Okay, sorry. So, say the B, if we look at the load in the modified schedule for an assignment S, okay, that's just B times that is going to be the sum of the modified weights, B times the sum of the modified weights for all the jobs that get assigned to machine I in that schedule. Well, the modified weights were just dividing by B, but then rounding up to the nearest integer. So I'm saying on the one hand, this rounding up only makes things bigger, so it's at least, you know, if we just cancel the B's and sum up the original weights, we get something smaller. So then that's going to say that this B times this new weight is at least the original weight, or the original weight is at most B times the modified weight. Okay. On the other hand, rounding up doesn't make it too much bigger. Rounding up and something to the nearest integer only increases it by at most 1. So we can give an upper bound on the same sum, just adding in 1. How many, so this part is the same as this part. Without the 1s, it's the same. And then we have at most n ones that we're multiplying by b, and we work things out so that n times this error is still small compared to the optimal solution.
The only epsilon term is this one, right? Everything else is symmetric.
Yeah. So this is just, so this is saying that the load in the original schedule is at least the scaled up modified load minus epsilon times the optimal. So saying we can use, in other words, we can use b times the load in the modified schedule as a very good estimate for the load in the original schedule.
And you've got a greater than or equal to, but I think you mean less than or equal to right in front of that.
So
On the second line, right?
what I mean is that this part is greater or equal to this part.
Okay.
Well, let's look at the optimal schedule in the original job, and here and then we have our schedule, which is optimal for the modified schedule. And I want to say that the workload here in the original schedule isn't much bigger than the work over here, than the cost over here. Okay, so so the make span in the original schedule of our solution is the maximum of load 1, load 2 of our solution. And we said that that's at most, so b times the modified loads of our solution. So the max of b times load 1 of S bar, load 2, b times load 2 of S bar. Okay. But we know that our solution for this modified problem, so this is equal to b times the max. This is the make span for our solution in the modified problem. But we got this solution by finding the optimal solution for the modified problem. So this is the best it can be, and in particular, when we compare it to the same thing for the optimal solution for the original problem, that's only going to be worse as far as the modified problem. So if we plug in now we can go to the optimal solution for the original problem and say, that plugging in the optimal solution for the original problem, it isn't anymore the optimal solution for the modified problem. It maybe made things a little worse. Okay. But it didn't make things, okay, so, but on the other hand, okay, we said that b times the load in the S-opt, how does that compare to the actual cost of the load in the original schedule for S-opt? Well, we said it differs by at most this epsilon opt. Okay. So this is at most b, okay, so I should say the max of b times the load here, b times the load here, Well, that each of those by this lemma applied to S opt is at most the load in the original plus epsilon times the opt. And load 2 and we can bring out the plus epsilon opt, and this is actually, you know, the max of the load for the optimal solution is how we define opt. That's the cost of the optimal solution, the big span of the optimal solution for the original problem. So this is at most opt times 1 plus epsilon. So what we found was our solution, even though it was solving a different problem, a rounded off version of the problem, was within 1 plus epsilon of the cost of the arbitrary solution, of the optimal solution. Okay. And so we're finding a solution that's almost as good as the optimal solution. So where did we lose? Okay. Well, the only place we pay is that, remember, the time complexity was n cubed over epsilon. Okay. So we can make epsilon as small as we want, but we're going to pay in terms of the time proportional. If we make epsilon 1%, then we have to run 100 times as long. If we make epsilon 1 in 1,000, we'll get a solution that's within 0.1% of the optimal, but will take 1,000 times as long to find it. So this kind of trade-off between time and accuracy is called a fully polynomial time approximation scheme. So polynomial time approximation scheme means that for any fixed epsilon, there's a polynomial time error, polynomial time algorithm that approximates within that epsilon. Fully polynomial time means that the time we spend isn't like exponential with epsilon, it's only polynomial in 1 over epsilon. So if you can't find an optimal, if finding an optimal solution is hard, then a fully polynomial time approximation scheme is about as good as you're going to get. The least glamorous sounding problem in computation, you know, in theory of computation, it's all about a system of pipes, and you're sending junk through the pipes, and you're trying not to burst any pipe. So, but what makes the flow problem important is that not only does it have a non-trivial algorithm, but it turns out that a huge number of basic optimization problems can be reduced to network flow, can be viewed as special cases of network flow. And this includes problems that you wouldn't think involve things flowing at all. So if you could recognize hidden network flow problems, that gives you a strong algorithmic tool to address a huge number of seemingly unrelated problems. So in this, how do we picture a system of pipes? We're going to have like one place in this network where things can flow in, and one place where things can flow out. And other than that, we're going to have some amount flowing through the pipe, but whatever flows into a node has to also flow out of the node. So the except for the intake place and the outgo place, there's conservation of matter. So, and then how do we handle, not bursting any pipe? Well, we give each edge a capacity. I'm going to make it directed edges, and the capacity in the two directions might not be identical, okay, even if you have an edge in both directions. So maybe you have capacity 3 going from C to D, but capacity 5 going from D to C. In this case, we won't, since D is our outgo node, actually we won't actually be using anything going out of D. So let's maybe put in an edge here. So let me write down more formally what the problem is and what the constraint. With non-negative edge weights, and the edge weights are called the capacity of the edge from U to V. We're given a starting place and an ending place. This is called the source, and T is called the sink, and they're both in the set of vertices. And the constraints are, the type of object is we have a flow. It's also going to assign for every directed edge an amount flowing. From U to V. Okay. There are two types of constraints. Okay. One is conservation. For every node U that's not the source or the sink, the sum over V of the amount flowing into the node has to equal the sum of the amount flowing out of the node. Okay. And then there's the capacity constraint. For every edge, E, the amount flowing through that edge is going to be upper bounded by the capacity of that edge, or else the pipe bursts, which is bad. Yeah. Okay. And what we're trying to do is maximize the total amount flowing from S to T. You can say that the flow of F is going to, because of conservation, anything that flows into S has to come out of T. It can't go, it can't end up anywhere in the middle. It has to eventually flow into T. So if we talk about the amount flowing from S to T, that's just the same as the amount flowing out of S. It's just the sum over U of the amount flowing out of S. And I should say, just to keep things simple, well, I guess we could, technically we need, there really is no point in having things flow into S, but we haven't ruled it out. So I'm going to subtract off the amount flowing. If we have like circular flow around S, I'm going to subtract off the amount flowing into S. Just so that we don't have to put a rule saying nothing flows into S. Yes? Capacity. And that's saying we can't over utilize any particular edge. Okay. So even though I've talked about it as pipes and stuff, even directly, flows come in, like in computer science, you have a network, and these could be communication links, and then the capacities of edges are the bandwidth of the available links. And now you're trying to send information from the source to the destination. But you don't have to send it all via the same path. So it's kind of a generalization of the max bandwidth path problem where we're allowed to split up information and have it dispersed along different paths. Is this clear? Okay. So, okay. So we're going to look at the sort of basic network flow algorithm was invented by Ford and Fulkerson in the 50s. Okay. And then there have been like modifications of that algorithm to make it faster ever since. But they often utilize some of the same basic ideas. And there's also the general theory of network flow was sort of best established. The connections to some other related problems is best established by considering the Ford-Fulkerson algorithm. So even though it's kind of prehistoric these days, there are much better algorithms out there. It's a good algorithm to start with. Okay. And what this is also an algorithm that illustrates what I'll call the hill climbing technique, which is used in more use in heuristics than in sort of analyzed algorithms. The hill climbing technique is to take a solution and keep improving it until you run out of ways of improving it. So, or out of easy ways to improve it. So, this is often, so when you think of it, we'll start with, viewing the solution space. We're trying to find the maximum point along this curve, or below the curve, so we like take some point, and we say, oh, well, there's some way of making it better. Okay. Now, we have to find some way of making this point better. Well, how about if I go over here? That looks a little better. Okay. And then, maybe at this point it's looking even better. Okay. So we always like sort of look in our neighborhood, something close by that might be a little bit better as far as the objective function goes. Okay. So what's the problem with this general technique?
Getting a local maximum?
You can fall into a local maximum. So here, maybe the top of this hill is even better than the top of this hill, but when we get here, there's no way of improving the place where we're at. We're stuck at a local optimum, and we're never going to get to the global optimum. So when you're using a hill climbing algorithm, we have to come up with some reason. If we want to prove that it actually is finding the optimum, we have to come up with some reason why it's not true in general, but it's true in this particular case, that the local optimum is the global optimum. Yes.
On the last one, flow F, it says S, U, D, S, T.
No, because saying that the way to see, and you know, all the conservation constraints and all the capacity constraints, and then we're going to try to improve it. So what's kind of a not very good solution, but it's definitely a solution that we could start with?
Would you do like random ways?
Okay, so in heuristics we could do that, like restart the algorithm, try to flatten the search space, do some convolutions. As in flow, we're not going to have to do that. It's going to turn out that there really aren't any local optima that aren't global optima. But we're going to have to prove that when we're done. It's not going to be enough to say, oh, now we've reached a local optima. It must be the optimal solution, because you could have this situation. It will turn out we get lucky and don't have that situation. Yes?
Maybe start with a flow with source that's outputting the sort of minimum weight edge in the graph. Sorry, I don't know what you're asking. You're asking for
How to start the algorithm.
Right, so if you start with, for example, in this case 2, you know that that's going to be able to get, because 2 is the minimum weight edge here.
Okay,
So I don't know if that makes any sense.
okay, so I think you're doing like the starting. You're doing the first 2 steps. Yes.
I was just going to say you could start with a depth first search and then find default to see if there's no duplicates.
Okay. So I think what we've got is what I'm asking for is just too simple. Okay, and you're already thinking about the second step. So that's where we're going to use depth first search and looking at the minimum weight edge, both. But just to get us started, seeing what's a completely trivial solution. Yeah.
Just the minimum of the start and end. What's their flow? That would be your
Well, we don't have any flow right now, so yeah.
Just no flow at all.
Just no flow at all. Okay, so what I think I would say, shooting for something just too simple, but we need most of you. But it's just the obvious thing. So no flow at all is certainly a flow. So if we're putting the 0 in front of the number to say, right, the first number is the capacity, sorry, the flow, that what we're using, and the second is the capacity. So if we start with all flow 0, for every edge, then certainly the amount flowing in is equal to the amount flowing out is equal to 0, and since the capacities are always non-negative, we haven't exceeded the capacity. But the value on the downside, the value of the flow we got is just 0, so it's not very impressive. So now let's say, okay, that's the trivial one. Now let's try to make it a little better. We said that, in the end, the flow is going to consist of sort of a collection of paths from S to T. Well, to get some flow going, let's find a path from S to T. And that's where we can use, breadth first search, depth first search, whatever kind of graph search we want. But then so let's say that we find like the path A to E to D. Okay, so that's the path that we found when we did depth first search. Okay. How much flow can we send along that path? 2. And why 2?
Limited.
It's the minimum capacity. If we tried to send more, then we'd burst this pipe. Okay, so we can send 2 flow along that. And now that we've sent 2 flow along that, I want to make a note to myself about I'm going to try to make a graph that represents not what we've done as far as finding flows, but what more is available to us, ways of augmenting our current path. Yes?
Why does 2 imply that the H E will also be 2? Because I could route it from E to B and then B to C
Yeah.
and C to B.
Well, so we could find other paths, but here we just found one path. And if we're only sending flow along that one path, to maintain conservation, the amount coming into E has to equal the amount going out of E. So in the future, we're going to also send it flow along other paths. Okay? But I want to keep track of what we've got so far and what we can do in the future separately. So let's make a graph I'm going to call the residual graph. Okay? That's going to represent our ability to send additional flow. So once we fix this flow, how much additional flow can we send in the edges? And there's going to be one tricky point. So we'll have the same nodes in the residual graph. And many of the same edges. But they'll have different capacities. So the edges that we haven't used so far will have the same capacity. This was like a 6. But how about these two edges that we've used for additional flow? How much additional capacity do we have going from A to E?
4.
4. How much additional capacity do we have going from E to D? 0. So we won't put that edge in at all. Here's the tricky point, is that unlike a greedy algorithm, where once we've committed to a decision, we keep that, in a hill climbing algorithm, we're allowed to change our mind. Okay? So how can we represent that we're allowed to change our mind about sending these 2 units of flow along these edges? We're going to put in edges that represent changing our mind, reducing the flow along those edges. Now, in this case, it might not really help us, but we'll put in those edges anyway. So what we'll do is we'll put in an edge of capacity 2 in the reverse direction, and we'll put in an edge of capacity 2 in the reverse direction here. Now, this is an edge going into the source, and this is an edge going out of the sink, so we know that they're really not going to help us, but this is sort of the general rule, so I want to keep on doing it consistently. Okay. So did you have a question before? Or? Yeah.
I was just wondering whether when we do this residual graph, we commit to this flow that we decided.
So I think no, and the reason why we haven't committed to it is we've put in these edges that represent the ability to change our mind. Okay. So if we in the future we use these edges going in the reverse direction, that's going to mean decreasing the flow in the forward direction. So we don't just keep on adding new edges. Sometimes we change our mind about edges that we've already existed. This is actually very important. If you didn't do this, we wouldn't actually reach the optimal flow. There are many cases where you have to actually, to find an augmentation, you have to reduce the flow that you currently have. Yes?
Why isn't everything bidirectional like the other thing you would say?
I could have done that. It's just harder to draw. And in fact, sort of in the algorithm, that's what I'll do to begin with. Just to when I'm describing the algorithm more formally, I'll put that in. It just would have created a lot of edges in the picture. Okay. So now we've got this residual graph. What do we do next? We want to, and we've got some flow. We've got 2 units of flow getting it from A to D. Now we want to send more flow. So what do?
Find another possible path.
We find another path, and in which graph?
In the residual.
In the residual graph. So let's see, so what's another path? We could go from A to F to E. Now we can't go to D because that edge now has been reversed because it was used to full capacity. Go B to C. Okay. And yes, I'm just using the more convoluted path. We could just use the top path. Okay. B to C to D. So how much flow could we send along that path?
3.
3, because even though almost all the edges are bigger than 3, it's the minimum capacity edge that determines. Okay. So, okay. So when we do that, we'll increase the flow in the original along that path by 3. And then we're going to change the residual graph by decreasing the forward edges along that path by 3. And putting in edges in the reverse direction with capacity 3 representing their ability to change their mind. I don't think that's going to happen now. Okay. So when we do this, and now we're trying to find a better flow, what's going to happen? There's no path to D. In fact, there's no edges coming into D anymore at all. This one got removed because it was used to full capacity. This one got removed. So we have 5 units from A to, we were able to send 5 units of flow from A to D along these kind of 2 distinct paths, kind of intersecting here, but but we can't send any more. So how can we argue? So now we're stuck. There's no way of locally improving our existing flow. But how can we argue that there wasn't any way of getting better at all? Yeah.
In the first residual graph that you created,
Yeah.
you missed one edge from B to E.
From B to E?
Yeah. Now there's a 3 or whatever, it's the reversing.
Okay.
Add up
I think I reduced the I see. So there was already
4. Yeah, what's already 3 or yeah.
Okay.
4 with it. There's a 4 and a 6.
Okay. So yeah, so I messed up. So what I should have done was
Increase to 6.
increased this 4 to 7 in the residual graph. Instead of inserting an edge of capacity 3, if there was already an edge,
So it should be 7.
I'm getting confused. Okay, so let's see. So we're sending 3 of the 4 in this direction, and we got it. We know we can't get any more by this augmentation process because this edge is used to full capacity and this edge is used to full capacity. So in retrospect, can we argue that we couldn't do better than 5 just by sort of looking at the original graph?
That's true. Okay.
So, look at the edges that were used to being currently used to full capacity. And what does that say in the original graph?
That was your limit.
So, this in the original graph had capacity 2, and this edge in the original graph had capacity 3. So what would happen if we tried to send more flow into D?
Okay.
One of those edges would burst. So we found kind of a matching upper bound. When the algorithm terminated, not only did we find a flow that we couldn't know how to improve, but we found a sort of matching bound in terms of a set of edges that would disconnect D from the rest of the graph.
What
makes the algorithm terminate? How does it know not to go back and?
Okay, so we have to, well, so that's a good point. So how do we know the algorithm terminates? Does the algorithm terminate? Or when does the algorithm terminate?
I think it's this thing.
So,
No more path.
yeah, so, okay, so let's, you know, and then what does that say about the running time of the algorithm? Yeah.
I just have a question. When you
Method on a graph G, capacity C, a source and a sink does. So first, for every edge U to V, we're gonna, if the edge from V to U is not in E, add it with capacity 0. So that, then all the edges are in both directions, but some aren't actually in the graph. But it's going to be handy to have at least a virtual edge for every edge, going in the reverse direction for every edge, so that we can define so it's residual capacity in the other direction. So we initialize the flow to 0 for every E, and we repeat until the depth first search fails. So we're going to define the residual capacity of an edge to be the capacity of that edge minus the flow along that edge, but plus the flow along the reverse edge if it exists. So if we're actually sending flow in the other direction, that increases the capacity in our direction because we have the right to change our mind and decrease that flow. Okay. So for every E, we define this. The GR is going to be the set of edges that. So we want to not use, when we try to find a path from S to T, there are certain edges that we can't use. Which edges can't we use?
Wait, say it again?
If the residual capacity is,
Negative? There,
well, we're going to never have it be negative because that would be a violated constraint, represent a violated constraint, but it might be 0. In that case, we can't use it anymore. Okay. So we're just going to look at the set of edges with residual capacity bigger than 0. And we'll find a path from S to T in G sub R. And then so
So we need to take them in.
I think so.
You
Because
literally just take them in with the path.
we do the min of the path. But I'm saying, like, if we decided that we're going to send 3 units of flow along the path, and we currently have 2 units flowing in the reverse direction, okay, that's, we must have had at least 1 unit of capacity in the forward direction to get a residual capacity of 3 in the forward direction. But what we'll see is that what we'll do is reduce this down to 0 and increase this up to 1. Okay? So I don't want to like decrease this down to -1. It sort of would be equivalent, but same. So, but on the other hand, if there were 4 in the reverse direction, and we were sending 3 through the edge, we would decrease the 4 down to 1. So the net change is always 3, is always the amount that we send forwards. Yeah.
F minus the both that word?
F minus the above quantity.
Oh, okay.
So this expression. Okay. So saying so what this says is, well, if the minimum is F, this is going to be 0. So if the flow in the reverse direction is bigger than the amount we're changing it, we just decrease the flow in the reverse direction and don't change the flow in the forward direction. If it's smaller than F, if it's 0 in the other direction, we just increase the flow by F. If it's smaller, we decrease the flow over here until it's 0 and take the remainder and increase the flow in the forward direction. Okay. And since, yes?
Can you just clarify some notation? What does e to the r mean?
So I'm using e to the r to mean the reverse of this edge. So if e equals is the edge from u to v, er is the edge from v to u.
Okay, and then c sub r, is that
Oh.
capacity of the reverse edge? Is that what that is? Or should that be c of e to the r? The minimal c.
So maybe I should use a little r here, because this doesn't, one is reverse and one is residual. They don't have no connection, no logical connection to each other. So, but this is the actual flow along the reverse edge. So every time we could, recompute all the residual capacities based on our current flow. Now, it would be more efficient to keep track of the residual capacities and update them as needed just along the path. The ones not along the path don't actually change. Hopefully I got the R's right. Okay. Yeah, really that. Okay. So, okay. So when we terminate when we can't find a path that augments the flow. So I only have a few minutes left, but let me just at least prove that under certain circumstances this algorithm terminates. So how do we know? Okay. So say that ft is our flow after t iterations, and say that all the capacities are integers to start with. Okay. Then what can we say about the flow after one more iteration? So one thing I should say, one nice thing about this algorithm is that if the capacities start as integers, then this f is always going to be an integer. The residual capacity, that means the amount we change the flow, is always an integer. And so the residual capacities stay integers. And so everything in the picture stays integral. Okay. So if we start with integers, then what can we say about the change in the flow?
Greater or equal than 1.
is greater or equal to 1. Because it's always bigger than 0, and it's always an integer, so it's always at least 1. Okay. So that's saying that, after t iterations, the flow that we have is at least t. And on the other hand, what can we say about an upper bound on the flow?
Summation of all the
Incoming edges. So it's like the sum of the capacities of the incoming edges into t, for example. Okay. So this is some bound, each of these is some fixed integer. So in particular, this means that the algorithm is going to terminate within this amount of time. So the number of iterations of the algorithm is going to be at most the size of the flow that we get, and the size of the flow we get is at most the sum of the capacities of, say, the edges coming into t. Now,